It's a pleasure to be here after 10 years again in Kosovo and to meet a lot of friends. So I'm sharing today the work that we do at Erasmus MC in Rotterdam, so about the detection of cone photoreceptors in adaptive optics. I will not explain how the technology works, how the wavefront corrections work, because this was already discussed in other talks. But I would like to mention that we used the RTX1 adaptive optics camera, which pretty much corrects for the aberrations that result from the anterior segment of the eye, and with that we can just increase the resolution of the images that we get, and can go in vivo microscopic imaging. And so when we get like an image with this camera, so it looks like here at the center, so it looks very small. So it looks very small, so it's 4 by 4 degrees, so you can see how it compares with the SLO image, which is 30 by 30, or even with a wide field color fundus image, which is, in this case, the 133 degrees. So this means when we acquire this kind of images, you always need to acquire a couple of images in order to create like a montage. And the way how people do montage so can differ, so depending on your use case, on what you want to do with these kind of images. So this is the protocol that we have at Erasmus MC, and we designed this for our case, which is focused on retinitis pigmentosa. Nevertheless, then what you do is just create a montage, and this is the resulting of the montage. And for instance, you can just focus on a specific part of the image, and then you can see this kind of structures here. So this information are the cones, so you can see all of them there, and what the theory says is that the information that we see here of the cones just comes between, from the information between the inner and outer segment of the cones, so here. But then the question is, okay, we have these nice images, and actually adaptive optics has been in the market for a while. 10 years ago, it was already in the market in the same, when we were at the same VPO here in Kosovo. But the question is, how can we extract information from these images? How can we make this useful for the clinical practice? And so there is some software, and the gold standard actually is the AO-Detect. So the majority of the papers that you find in the literature, so they use this kind of software from Imaging Eyes, which is a robust software, it's nice software, it shows a lot of results, but it has a limitation, which is the region of interest. So it's limited to 80 by 80 pixels. And in this specific case, which is a 4 by 4 degrees image, the size of the image is 1500 by 1500 pixels. And in our case, which is a montage, so it's 9000 by 6000 pixels. So which makes this kind of analysis very difficult in our specific case. So our work is about this, so it's about to explore, develop, and validate automated approaches for analyzing the cone photoreceptors in these kind of images. In Rotterdam, we already developed a kind of long pipeline, which I will not explain everything here. I will just briefly mention. So let me just guide you through. So we select a couple of images first, and then we just do a kind of image selection based on signal to noise ratio and other parameters. We do the vessel shadow segmentation, and then we divide the images in different kind of patches. And based on these patches, then we do a kind of classification. We say, look, there are cones in these images that we can either segment, or there are no cones. And if there are no cones, then what we do is unsupervised pattern recognition. So we just divide different kind of patterns which are linked to different kind of diseases. I will not cover this part here. I will focus on the upper part, which is the automated detection of the cone photoreceptors. So for this part, we started with a data set of adaptive optics images. We divided it in patches, as I said, and then we divided it in training and testing set. And for the testing set, so we had specific overlap as well in the patches in order to calculate the intra-grader agreement. Then we had like 4 graders. So the training set was annotated by 2 different graders from Erasmus MC, but the testing set was annotated by some 2 graders, but also graded from University Hospital of Ghent and another one from the Western University of Australia. And I must say the interesting part here is that one grader had 3 months of experience and another one had 10 years of experience. And then once we shared the images with the different graders, there was this question is like, I mean, although that we look at the images and we see the cones, but then there are specific cases that we are not so sure whether it is a cone or not. And the problem of these images is that there are no standards for what should be considered a cone. So this has been the problem in the field actually, and the limitation for including it in clinical practice. And so what we did was to came up with something very simple. So we said that let's make something, the first rule, something that we can share with the graders, then let's see how it goes. So in this case was that we said that the cone should be like a round characteristic structure, and it should have like intensity peak, which should follow more or less a Gaussian distribution, and it should have like a similar size and spacing compared to the neighboring structures. And this is similar, not like a fixed, because the size of the cones also change from the fovea to the periphery, and this is something very important as well. So then, the question was, so what kind of quality or metric can we use to evaluate then the performance of our model or to compare the results of the graders? Because as you can imagine, it's such a problem when you do the annotation, even if you are just a few pixels from the center of the cell, it's still the same cell, but when you use like other metrics like die-score, will not work. So what we did was just to set our own metric, and it was based on a radial distance. So if it was within a certain distance, the second dot, then we call it a true positive. If it was not the case, it was a false positive. And then based on that, we could calculate the precision recall, and then we used the F1 score as our evaluation metric. Right, so then we proceeded, so then we just trained UNet. So this is the basics or the standards in terms of image segmentation. So did the hyperparameter optimization, something that Alejandro was also trying to explain today as well how it works. And then we checked the intra and intergraded agreement. But let me make one step back, because then we had the results of the model, and we wanted to know how good the model was. Because when you check in the literature, so there are no AI models so far published for the detection of the cones. And a way to see how good the model is to look at intra-graded and intergraded agreement first. And what we saw is that for the intra-graded agreement, so it was for the F1 score, so it was 85 around the fovea, then going down up to 80 in the periphery, and the intergraded agreement was not so different from that. So in the case of the periphery was 76%, which is good because I said before that we had a grader with 3 months of experience and another grader with 10 years of experience, which means that the annotation criteria that we were giving to the graders was doing a nice job. So then we had these kind of values, but still we wanted to have a ground truth. And the way how we defined the ground truth was pretty much with a voting system. So if 3 graders say that, 3 of the 4 say that, okay, this is a cell, then we consider it a cell. If they were not agreeing between them, we said that this is not a cell. And then what we did was, after creating that kind of ground truth, we compared it with our model. And the results of the model were very good, so it was 87% around the fovea, 81% so in the periphery, and we also compared it with AO-Detect, which is the gold standard in the literature. And we saw that the model performs much better than the AO-Detect, so the manufacturer software. Mainly in the periphery, and I also must say here, uncorrected for the AO-Detect, and this is very important. Because AO-Detect is also software that should be a semi-annotation tool, and a lot of times when we see like papers and literature, people just don't take that in account, but it's something that is important to mention. Software does the annotation, but you should always do also the correction of that. Alright, so then this is the result of the prediction, so of the model, so you can see how it performs here more in the periphery, but you can also see how it performs when you have like a vessel shadow. So you can see that it's not predicting pretty much where you have the vessel shadows. It's not, the cones are not there, it's just, there isn't just no signal there. And then we create like a density map, as you can see here, so you can see that the density of the cones is increasing as you approach the fovea. And then we also run it for the entire montage, so which was our protocol that I mentioned at the beginning. And by doing so, by running our models, so this is how it looks like. So you see the density with red, that's the highest density of the cones. And you may notice right now that at the center here, we should have actually the highest density of the cones, and that's not the case, right? It's not because of the model is not working nicely, the model is working, but it's because of the imaging technology doesn't have enough resolution to detect all the cones. So as you might know, so the cones, the spacing between the cones is very small, and then the resolution of the device is of 2 micron. Nevertheless, this information, and by building normative databases, can still be used to correlate with diseases. For instance, if you see an increase here of the cones, it may mean, for instance, in case of Stargardt disease, where you start to have like spacing between the cones and now you are able to detect. So it's like you are losing cones actually. And finally, can we bring it a step closer to the clinical research? Because a lot of times we, like scientific researchers, we do a lot of nice tools or nice software, but it never reaches the clinical research. And I think that we also have the obligation to bring it a step closer to the clinical research, to ophthalmologists or optometrists. And that's what we always try to do, and for that we developed a software, which I'm showing now for the first time, and where you can just like pretty much import folder or just a single image. You can select the model that you want to run. So you can just select all the images. So you can detect montage for a single image. So you see here that it's like running the model for the images, so you can just let it run. So if you just open one of the images, you see the montage, you see the prediction, you can just zoom in if you want. You see the vessel shadow segmentation, which is another model that we have implemented. Then you also see the cone density, and then you can also extract metrics of the cone density as a function, or once you detect where the fovea is. And pretty much this summarizes the work that I want to share here with you today, and I would like to thank the people that also collaborate with me from Erasmus MC, Sander and Luise, and people from Rotterdam Eye Hospital, and from University of Ghent, Lions Institute, and Imaging Eyes as well for the support. Thank you.
A question, but I see a problem with RTX1. I was very eager when it was introduced to the market, but the problem is that you can get good images of high quality when you have young subjects, young patients. When people start cataract, early cataract, almost invisible, for example in an optometric examination, then this machine gives very difficult to analyze images. So if you think about clinical application, there is a natural problem. The pathologies usually are age-related, but also cataract is age-related. So you cannot analyze the state of the retina in this way when you have, for example, a 60-year-old patient. Okay, so it's always a question how to use it to not partially, but to have very good technique. But it's of course very interesting. It's worth developing. But could you comment on this problem of scattering light in the intraocular lens that makes the images much worse?
Sure, definitely. So cataract, for instance, is an issue, and but it's also an issue like on fundus imaging normally. right? So usually you should use RTX1 when you are able to acquire nice images with OCT or fundus images. If you are not able to acquire nice images with those, you shouldn't be using the RTX. And actually, I would say that the advantage of this technology is for the early detection of diseases, actually. And it has a lot of potential in diseases like retinitis pigmentosa, Stargardt's, where you don't see any changes in the photoreceptors layer in OCT, but you can already see a decrease in the cell density, for instance, in OCT. And it has also other applications that we are working in Rotterdam, which is to see the recovery from after of surgeries. For instance, in macro how the photoreceptors recover after the surgery, and we get like really nice results. We can see the follow-up. We just don't see differences only in the OCT itself, but we see differences in the AO images. And I think that AO has a lot of potential, but we just need to point, let's say, the highlights to the right direction as well.
Okay, thank you very much. I think that it underlines the current opinions in the bibliography that multimodal techniques are the future, because each technique has its own limitations, but if you combine, for example, OCT with some other techniques, you can get something that is very, very useful.
Yes, let me just add to that there is a device that the M2 OCT that also combines adaptive optics with other imaging modalities, with OCTA, OCT, and SLO, and you can get really nice images from that.
Thank you very much.
Please thank the speaker again.